All right. Aha. Okay, you escaped the plague upon your house. I was talking about how we have a dearth of attendance today, and so I said a plague upon their houses.
Just in time.
Just in time, that's right. Yep. Just in time attendance, as it were. Okay, so finishing up last time, we were talking about how in quantum mechanics we can have degeneracy, we can have multiple quantum states that all have the same energy, and one that's of particular importance to us here is hydrogen, good old hydrogen. And so strictly speaking, it's not quite true that the energies in the hydrogen spectrum depend only on N for a free atom. There's also an L dependence due to what's called spin-orbit coupling and some relativistic effects, but doesn't matter much for our purposes here because the energy differences are exceedingly tiny. That's the hydrogen hyperfine structure. So we'll take the energies only to depend on the principal quantum number n. And then last time we were talking about how we had these rules that L, right, goes L, okay, well, so N is equal to what? What's the lowest possible value of N? Remind me? Not 0, 1, 1. And then next comes 2 and 3 and 4 and so forth. That's integers, right? 1, 2, 3, there's the pattern, right? N, okay? L goes from, what's the lowest value? 0, 0 to, what's the largest value it can have given n? N minus 1. In steps of 1, I'm not going to write that. It's integers 0 to n minus 1 in steps of 1. And then we got m sub L for the z component of the orbital angular momentum. And for a given value of L, it goes from what value to what other value in steps of 1? Minus L to plus L in steps of 1. Goes from L minus L to L in steps of 1. Again, I'm not going to write in steps of 1. That'll be understood here. And then finally, we've got the spin quantum number. And for an electron, the spin quantum number can be, what two values? Plus 1/2, minus 1/2. It's really the z component of the spin. So m sub s is plus or minus 1/2. And so the fact that the energies only depend on n, whereas L and m sub s can have all these values, means we've got degeneracy, means we've got multiple possible quantum states that all have the same energy for an electron in a hydrogen atom, and we can enumerate them with what we call a tree diagram. So in other words, we can start off with n. So here's n equals 1. If n is 1, what are the possible values of L? If n is 1, L goes from 0 to n minus 1. So L has a maximum value of what if n is equal to 1? 0. So it goes from 0 to 0 in steps of 1. In other words, L has to be 0. And then for m sub L, if L is 0, m sub L ranges from what to what? 0 to 0, right? Because minus L to L, m sub L can only be 0. But for m sub s, we've always got two possibilities, namely 1/2 and minus 1/2. And I'll just say plus 1/2 to emphasize. Plus 1/2 and minus 1/2. And so we can make a list of the 4 quantum numbers that correspond to these two states that we've enumerated here. In other words, we'll make a listing here of n, L, m sub L, m sub s. And if you know those 4 quantum numbers, you know the state of the electron. So here we just follow everything. 1, 0, 0, 1/2. 1, 0, 0 plus 1/2, and then 1, 0, 0 minus 1/2. And so then we can also say the degeneracy, the number of quantum states that have that same energy, we'll call that G sub n, the degeneracy associated with a given value of the principal quantum number n. So here we've deduced that G sub 1 is equal to 2, because there are two states that have that same energy. G sub 1 is equal to 2. And as a reminder, I'll just add this too. E sub n, what was our formula? Good approximation for E sub n in hydrogen? It's something over something squared. What is it? Chirp, chirp, chirp. Oh, those crickets. So it's minus something over something squared. What's squared in the denominator? N. So it's that, and then burn it into your brain. What over n squared? No. Close. So close. 13.2. No. 6. There we go. Minus 13.6. What are the units? EV, 13.6 electron volts over n squared, minus 13.6 electron volts over n squared. So that minus 13.6 EV is the ground state energy for hydrogen. Oh, you should so remember that number. And so E sub 1 here is then equal to what? What's the energy of the ground state? We just said it. What's minus 13.6 over 1 squared? Quick, quick, what?
Minus 13.6.
Minus 13.6 EV. So in other words, hydrogen has a ground state energy of minus 13.6 electron volts, E1, and there are two states with that energy because one has spin up and the other has spin down, basically. Because the L and M sub L are both 0. And what is our other name for this state? In other words, in chemistry, what do you call the n equals 1 orbital? What is L equals 0 called in chemistry? And even in physics, too. What letter designation do we give L is equal to 0? Okay, think back to your chemistry class. Ground state of hydrogen, you said that's the 1 orbital. What letter? What? Now I'm coughing, yeah. Right. That's the 1s state there. Right? In chemistry speak, and physics too, but chemistry speak, you'd say, oh, you got the 1s orbital and the electron can be spin up or spin down in it. And so the degeneracy is 2 because you got two states, spin up and spin down, that both have that same energy. What questions do you have? Shall we do n equals 2? Yes, we shall do n equals 2. So if n is equal to 2, what can L be? 0 or 1, right? Because it goes from it goes from 0 to n minus 1 in steps of 1. So I'll just put the larger value higher up. So L could be 1 or L could be 0. So now our tree has a branch, our trunk branches when we get to L. If L is equal to 0, ML has to be 0. But if L is equal to 1, ML can be negative 1 or 0 or 1 because it's minus L to L, right? So M sub L, if L is 1, can be 1, 0, or minus 1. And then I didn't leave enough room, so this is going to slant a little bit. So each of these can have the electron, so here's these states, right? And the electron can be spin up or spin down in each of them. So I'm not going to list them all, but I'm going to draw a little extra branching there, right? I'll put on the top here, +1/2 for MF minus 1/2. And I could do the same down the line. I could do the same down the line, and then we could come over here and list all the possibilities. Maybe you line them up better than I am. I didn't draw it so that they would line up. But in other words, we can go and read off all the values, right? So there's a state with n is equal to 2, L is equal to 1, M sub L is equal to 1, M sub S is equal to +1/2. That's what we'd get by always taking the upper path on that branching thingy there. So you'd have 2, 1, 1, +1/2. But there's also 2, 1, 1, what? -1/2, right? N is 2, L is 1, M sub L is 1, M sub S is -1/2. 2, 1, 1, -1/2. What would be the next one I would list? I could go, I mean, I could list these in any order, but I could go So if I do that, I get, say them out, 2, 1, 0 +1/2. So in other words, if this is the trunk, here's the leaves, and we want to see what's written on every leaf. And what's written on every leaf is all the numbers that came before that. That's the idea here. So we got 2, 1, 0 +1/2. But then also 2, 1, 0 -1/2. 2, 1, 0 -1/2. Maybe you're on your page, you'll just keep going down. But I can't go down. I'd be writing on wood. Nobody wants that to be hidden for most of you. So what's another one I could list here? Well, I go, what is this leaf right here, in other words? So it's this, 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 this. So it's 2, 1, -1, +1/2, right? So we've got 2, 1, -1, +1/2. 2, 1, -1, -1/2. -1/2. And then we've got so we've got 2, 0, 0 +1/2. Spin up for n equals 2, L equals 0, M sub L equals 0. M sub S is +1/2, spin up, and then finally 2, 0, 0 -1/2. Okay, and so what is G sub 2? What's the degeneracy? All these states have the energy, same energy, because the energy only depends on the value of n. How many states did I just list? 8. So G sub 2, the degeneracy for n equals 2 is 8. And what is E sub 2? What is the energy of those 8 degenerate states?
Negative 30.6 electron volts over 4.
Over 4, right. Minus 13.6 electron volts over 2 squared. Energy sub 2 is minus 13.6 electron volts over 2 squared, which is minus 3.4 electron volts. If I'm recalling correctly. Was that right? 4 times 16? Yeah. So minus 3.4 electron volts. So I don't feel like writing the whole thing here, but well, we'll set up the idea here. So if I go to n equals 3, right, if you do n, l, m, l, ms, we're not going to list them all this time, but just, sure you get the pattern. So if I have n equals 3, what are my possible L values?
L values?
L values, yep. 0, 1, 2, right? It goes from 0 to n minus 1. So 0, 1, 2. So 2, 1, 0. And for L equals 0, what's m sub L? 0. And then there's always the spin branches, right? Plus a half, minus a half. For 1, what are the MLs? Right, minus 1, 0, 1. And then there's always the two leaves that come out at the end for spin. And then for 2, L equals 2, it's a minus 2, minus 1, 0, 1, 2, right? So things get more and more crowded here, right? Minus 2, minus 1, 0, 1, 2, and then right? Each one of those has spin branches. So I wasn't very careful about leaving the right amount of space or whatever. But we could do exactly the same thing now and list all the quantum numbers if we want to know how many states there are without bothering to write out the lists. There are 1, 2, 3, 4, 5, 6, 7, 8. 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 states this time. So G sub 3 is 18. There are 18 states all that all have an energy of E sub 3 is minus 13.6 electron volts divided by 3 squared, which is something. What is it? 1.51. So minus 1 point, thank you, minus 1.5 electron volts. And we could keep going, right? Every time we go to another n, we add another possible L, which goes from we add another possible L, and then we have MLs that go from minus L to L. So if I went to n equals 4, I could have L equals 3, and then ML would be minus 3, minus 2, minus 1, 0, 1, 2, 3, and so forth. There is a pattern here, namely, the degeneracy is, and I'm debating with myself whether I have you do the proof of this. You can prove this fact by induction. Have you done proofs by mathematical induction before, where you show it holds for n equals 1, you show that if it holds for n, it holds for n plus 1, and then you've proved it holds for every value of n, because you've constructed the ladder, so to speak. So one of the problems in the book is to prove by induction that G sub n is equal to 2n squared. I might give you that, just give you some practice with mathematical induction, and then you can joyfully show that this is true. But here I'll just quote the result. G sub n is equal to 2n squared for hydrogen. Because notice that indeed G sub 1 is 2 times 1 squared, right? G sub 2 is 2 times 2 squared. 2 times 4 is 8. G sub 3 is 2 times 3 squared. 2 times 9 is 18, and so on and so forth. So, right, physicists, we often do proof by pattern. Wow, I did it for the first 3 and it worked every time. It must hold all the time. But there's a very good 3 Blues, 1 Brown video where he does a song where he shows all these things where it's like, oh, wow, this is working, what? It stopped working, right? So really you need to do a rigorous proof. It doesn't work to show, well, it holds in several cases, so it must hold all the time. I see the pattern. Of course, you really have to do something like a proof by induction to show that it really, truly always holds. That video has some really surprising ones where it's like, wow, if I did a few examples, I'm sure this is true. I'm sure mathematicians could, what? It's not true? It suddenly broke? All right. Anyway, what questions do you have? Okay, we're going to take a detour now. Oh, wait. What'd you go to sleep for? I have to tell it to stop doing that. Hey, wake up. Give me a prompt. Yo, what's up with that? You're plugged in? Hey. Oh, I muted this, so I'm probably getting the login prompt over there, which I'd rather have it over here. There we go. Okay, so, uh-oh, you're going to know that my password is ... right? Yeah. Yeah, all my passwords are ... Okay, there we go. Okay, so now we are going to go through the Astronomy 111 level description of how we can deduce that basically hydrogen spectral lines should be most prominent in stars with a temperature close to around 10,000 Kelvin, and weaker in both hotter stars and cooler stars. And initially, astronomers thought, well, stars that have more hydrogen in them would have stronger hydrogen lines, until Cecilia Payne came along and showed, as I alluded to last time, no, that's not it. It's the temperature that's causing those differences, and that all normal stars are made primarily of hydrogen and helium. And so I'll give you the kind of somewhat qualitative description of all that so that you see the forest, and then we'll go down into the trees and put the math behind it. So first Astronomy 111 level, then Astronomy 310 level, where we go into much more mathematical detail. Because I think if we just do the mathematical detail, you'll be kind of like, what is the point of this? And you're kind of like, where is this headed? So I want you to know where we're headed first. So I think we mentioned this last time, right? Why do stars have absorption spectra? So again, we'll in much more detail explain how this works later, but just as a reminder, the basic idea is that the star's outer layers, what we kind of call its atmosphere, even though in a sense a star is all atmosphere because stars are gaseous throughout. It's too hot for anything to be solid in a gas, except for the coolest stars, which might have tiny little kind of like dust specks in their atmospheres. So you've got the upper layers of the star are cooler and less dense than the deeper layers of gas below. Those deeper layers of gas, as we'll see later, because they are optically thick, produce essentially a continuum spectrum, essentially what's a good approximation to a Planck spectrum, black body spectrum. But atoms in the cooler upper layers of the atmosphere selectively absorb some of the light coming up from below, and so if you look at the star spectrum, there's light missing at those wavelengths, so you get a series of dips in the spectrum. You get an absorption line spectrum. If you were to take a photograph, then as we went out and saw before, you end up with a rainbow with dark lines crossing it from top to bottom. So did you know that the word computer is older than electronic devices that do calculations for us. The word computer used to mean flesh and blood human beings who were employed to do computations for people. And so here is a group of Harvard computers in about the year 1890 when this photograph was taken. So Edward Pickering was a Harvard astronomer who hired a group of talented women to help him out with doing spectral analyses and so forth. And so here is that group of women that were together in this room. I think this is probably a staged photograph, I'm guessing. But anyway, so the bad news was that in those days, women were not allowed to be professors. You can be a faculty member at Harvard. For what reason? Because it was 1890, right? It's not because women wouldn't be qualified to be so. The good news is Pickering hired all these women, and they've been given their historical due. They've been recognized for the really fundamental discoveries that they made, and we will be talking about a number of those discoveries as we go along. But for now, I call your attention to this person right here, because what she did is be responsible for the modern, most of the modern spectral sequence of stars. So this is, and names were so cool back then, Annie Jump Cannon. I mean, what a name, right? Jump, it's probably, I don't know where Jump comes from. Maybe it's like the family name of somebody else in her family or what, I don't know, but it's like Annie Jump Cannon here, right? So she became an absolute expert on classifying stars according to the strengths of their spectral lines. It's said that she could classify a star by looking at a spectrum at the rate of about 3 per minute. I've tried my hand at this before, and I would do more like maybe 3 per hour or something like that. So she got really good at this. She in the end, classified hundreds of thousands of stars. So Pickering had made a spectral classification sequence based on the strengths of hydrogen spectral lines in the star spectrum. And by the strengths, I mean essentially how dark they are, how much light has been removed relative to the surrounding continuum, the surrounding normal brightness wavelengths. And so here are a bunch of, I think these are really synthetic. I don't think these are genuine photographs. These are like computer-generated synthetic stellar spectra, but they are representative of what the stellar spectra actually looks like. So here's the H alpha line, which you remember is that red spectral line caused when electrons either, well, if you see it as red, it's because they're jumping down from n equals 3 to n equals 2 and emitting that deep red wavelength. But in the star spectrum, what's happening is stars in the outer atmosphere, which are already with the electron in level n equals 2, absorb a photon of just the right wavelength and jump up to n equals 3. And so there's that red light missing at that wavelength. So here's H alpha, H beta, the lovely tealish colored spectral line, H gamma, H delta, and then here in the infrared, in the ultraviolet, H epsilon, and so on and so forth, all these other spectral lines of hydrogen. And the thing to notice here is that they are strongest in this listing here for this spectral type right here, which this one's at 10,800 Kelvin. They're actually a bit stronger in spectral class A1 than that. But in other words, around 10,000-ish Kelvin is where the hydrogen lines are the most distinct. They're the darkest. And they are weaker, less distinct, at both lower temperatures and higher temperatures than that. So Pickering had originally classified stars with a letter system where A had the strongest hydrogen lines, followed by B, C, D, and so on and so forth. Well, Annie Jump Cannon comes along and looked at more than just the hydrogen lines, looked at other lines as well, and found systematic trends for hydrogen coupled with other spectral lines. And so she rearranged the spectral sequence into something that was more logical. And we now know it's a temperature sequence, but she rearranged it into OBAFGKM. So she threw out a lot of the prior letter designations and realized a more logical ordering when you look at all the spectral lines would be OBAFGKM. And you will surely want to remember OBAFGKM as the spectral sequence. And so I will share with you the mnemonic that has been handed down for generations. So, does anybody know what the mnemonic is here? Yes.
Oh, be a fine girl or guy.
Yeah, oh, be a fine girl, guy, take your pick, whatever you like. Oh, be a fine girl, guy, kiss me. This is the spectral sequence in order from, it was realized that it's a temperature sequence in order from hottest to coolest. So O-type stars are the hottest, M-type stars are the coolest. Dr. Andrick once put it to students in intro astronomy to come up with their own mnemonic, and the one that she liked the best was Ohio Buckeyes are football gods, kill Michigan. So, given that her husband was a dean at Ohio State for a long time, he's a physicist who was a dean at OSU, and she's a Buckeyes football fan, she enjoyed that one. My brother-in-law and sister-in-law, his wife, went to the University of Michigan and still live in Ann Arbor, so I should probably avoid endorsing that one, but I present it to you, should you care to use that as your mnemonic. I, being a kid who already knew that he was very interested in astronomy from a young age, memorized the sequence simply by pronouncing it. So that might work for you too. I just say O Baf Gookum in order to remember it. That works perfectly well for me. O Baf Gookum. It's relatively pronounceable, and so that's what I do. So our task, if you will, is to understand why it is that the hydrogen lines are strongest in stars of spectral class A, around 10,000 Kelvin, more particularly A1, and weaker at other spectral types. So before we get to that, I have to mention that pretty sure it was Annie Jump Cannon who did this too. It's further subdivided into, you add numbers to the spectral types. So in other words, for example, with type G, there's G0, G1, G2, G3, G4, G5, G6, G7, G8, G9, and then K0, and so forth. So in other words, we've got numbers as well, and as you go downwards, or as you go up in the numbers, you're going down in temperature. So that's why you see here, here's a G0 star, here's a G5 star, here's a K0 star, here's a K5 star. Not shown is there's also G1, G2, G3. Annie Jump Cannon, she was looking at so much detail that she said, oh, I can actually subclassify according to this numerical scale as well. And so that's the thing, in other words, if you're just trying to tell G from K, That's not too hard to do. But on the other hand, if you're trying to tell a G3 star from a G4 star, that's a lot trickier. And so what people would do is have standard like photographs of stellar spectra that were of each classification. And so you'd be shown like, okay, here's all these spectral lines for G0, here's all these spectral lines for G5, let's say, and you're trying to figure out what's this star spectral type. And you can say, well, this particular spectral line is stronger in this star than it is in G5, but weaker than it is in G0, and it looks more like the G0, so maybe this is G1 or G2. In other words, you look at lots of lines, and there's very systematic variation in the line strengths as you go through the scale. And so suffice it to say that you got to be very observant and careful in order to do that. And if you do a few 100,000 of these things, I guess you can get to the point where you can do 3 stars per minute that way. I will never, ever, ever get to that point because I do not care to try to classify several 100,000 spectra. But apparently she was born to do this, and boy did she do it. And so we have her to thank for our classification system like that. Okay, what questions do you have? Yes?
Are the other elements that Anija Khan looked at, are those all of them? Or was it just that she looked at helium and hydrogen?
Yeah, she looked at lots of different spectral lines. I don't have a list for you, but I'll show you in a minute a slide from one of the intro astronomy textbooks that I've used in the past that gives kind of general trends for these things. So, oh yeah, and I forgot. Would you like slides, a handout of these? Yes, that would be useful, wouldn't it? Because I doubt that you can reproduce these images that I'm showing here very well.
Thank you.
There you go. Yeah, just get all of your markers right and just make colors and draw, zillions of black lines. It'll be great. So, there you go. And for you. Yes, you're welcome. And for you. And for you. And for you. Yippee, there we go, yes. So, stars are classified according to the appearance of their spectra. Absorption line strengths depend mainly on temperature, again, as we'll explain. The full sequence is O Baf Gookum. The sun happens to be type G2 on this classification scheme. So we orbit a G2 main sequence star, and as we'll see, that the sun is main sequence means it is in luminosity class 5, Roman numeral 5, and it's also occurring to me. Hello, people watching the video. I hope you've been following along in the PDF of the presentations, all of the glorious slides that I forgot to zoom in on here for you. So, here we go. Zooming in there. Look at all those lovely spectra there. So, this is just a smaller version of the figure I showed before. Stars are classified according to the appearance of their spectra. Absorption line strengths depend mainly on the temperature. Sun is type G2. And the hottest stars are characterized by weak absorption lines of hydrogen and helium. Those are type O. In the middle, type A, strong hydrogen absorption. The coolest stars, type M. If you look at the type M stars, they're what we call blanketed by spectral lines. They're just like, oh my God, there's so many freaking prominent spectral lines for the coolest stars, type M. Coolest stars, their spectra are characterized by absorption lines of heavy elements or molecules. So those are stars that are cool enough that some molecules can form in their atmospheres. The sun doesn't have any molecules in its atmosphere because it's too hot. Collisions would break molecules apart. But the coolest stars, some molecules, some highly refractory, as in able to survive at high temperatures, molecules can survive. A classic one is titanium oxide, TiO, has a very it's a very strong binding, and so that's able to withstand fairly high temperatures. If we want to kind of see more detail, here's a plot of line strength, if you will, and this is, well, what does line strength mean exactly? You can do that in what's called the equivalent width. In other words, if real spectral lines, we'll see they're not infinitely sharp. They're not, it actually doesn't have to be exactly the energy difference between the two levels, because energy levels in an atom have finite lifetimes. And in quantum mechanics, there's an energy-time uncertainty principle as well. So other than the ground state, the energies of the states higher than that in hydrogen actually are not perfectly well defined. The energy isn't perfectly well defined. So there is some narrow, there is some spread in the energies, and that causes spread in the wavelengths that can be absorbed. And so a spectral line profile actually is like a dip, and the equivalent width, we'll get to it later, the equivalent width is how wide in wavelength would a perfectly black, 100% no light there at all spectral line have to be to have the same amount of light absorption represented by that as is absorbed in the actual star's atmosphere. So line strength refers to equivalent widths of the spectral lines. And the greater the equivalent width, the darker the line is, basically, subjectively speaking. And so you can see that, for example, for hydrogen, it's strongest at around A0, A1 or thereabouts, weaker in hotter and cooler stars. Oh, look, here's titanium oxide, which starting about like M1 or so starts to become prominent. That's that molecule that I mentioned that's highly refractory. As you get cool enough, more and more of it can form in the atmosphere. Here is calcium-2, which is prominent in the sun spectrum and not very prominent at all by the time you get to A-type stars. Now you might be saying, calcium-2, what is that? Some of you may know, and again, my job as an astronomer is partly to convince you, or at least to make you used to the idea that astronomers have some funny notations for things. So astronomers designate ionic species. In other words, an ion is an atom that has lost electrons. The neutral atom would have just as many electrons as protons. We designate atomic species, ionized species, with a Roman numeral that is one more than the number of electrons that have been lost. Okay, why is it one more than the number of electrons that have been lost? Well, you tell me, what Roman numeral represents 0? There isn't one. And so therefore, for the neutral atom, it was decided, let's call that chemical symbol for the element Roman numeral 1. That's the neutral atom, which has lost no electrons. And so 1 is one more than the number of electrons, 0, that it has lost. And so calcium-1, chemical symbol for calcium, Roman numeral 1, is neutral calcium. It has as many electrons surrounding the nucleus as there are protons. Calcium-2 is singly ionized calcium. 1 electron has been stripped from the calcium ion. What would calcium Roman numeral 4 be? How many electrons has it lost? Roman numeral 4, how many has it lost? 3, right? And so forth, right? 3. So, as an example where I happen to remember how many protons are in the nucleus, because I don't remember what it is for calcium, let's pick carbon, for example. How many protons are in a carbon nucleus? 6. So, what's C1? Why, that is carbon with how many electrons? 6. How about carbon 2? 5. Carbon 3. 4. Dot, dot, dot. Carbon. So, let's see. If I want to be that, right? So you remember how Roman numerals work, right? So it's 1, 2, 3. How do you represent 4? Yeah, it's IV. Sometimes I'll just write it with the lines all the way across. IV is Roman numeral 4 because V represents 5, and if you put something in front of a Roman numeral, it's a subtraction, and if you put something after it, it's an addition. So IV is Roman numeral 4, except on grandfather clocks, where for whatever reason it's typically 4 lines like that. Often it's used to do it, it's done that way. So then you've got calcium 5, so sorry, carbon 5. What is Roman numeral 6? So IV is 4.
Oh, it's V and I.
VI, right, so I say you got 5, 6, and yeah, I could just go like that, but I'm just feeling all fancy because in clocks they usually put lines right over. So you got 6, what's 7? Yeah, VII is 7, what's 8? VIII is 8, what's 9?
It's I and X.
IX, right, because it's 10 minus 1, and then there's 10, right, XI, XII, XIII, XIV, XV, and so on and so forth. One can readily determine why the Romans were a little bit stunted in their ability to develop algorithms for doing multiplications and so on and so forth. A little bit inconvenient to use Roman numerals for that sort of thing. Let's see, more fun. What is 100 in Roman numerals?
M.
No.
C.
C is 100, yep. What is 50? Do you remember? L is 50, yep. What is 1,000? M. What is 500? D, yeah. So what is 1888? Oh, the poor people watching are just seeing the screen. You're just listening to me. You heard me. I guess I should turn it to the things I do for you people. Walking all the way back here just to show all this stuff again. Let's see. Just kidding. Just kidding. I love you all, and it's my pleasure to help you learn by making these videos for you. So what's 1888, just for fun? What's 1888 in Roman numerals? Because that's a good year to write out. 1888, so we need 1,000 plus 800. So what's the first letter going to be? M, 1,800. DCCC, DCCC, because you get up to 3 symbols following in order to add. DCCC, 80. LXXX, LXXX, 8. VIII, 1888 was a fine year because it's MDCC, LXXX, VIII. Yes?
I have a joke.
Yes?
Why did Romans find algebra to be boring?
Why did they find algebra to be boring? I don't know. Why did Romans find algebra to be boring?
Because they knew that X is 10.
Because they knew that X is 10. Oh, God. Okay. Right. Yep. Gotcha. Nice. Yeah, did you ever see, I hope this is true, where there's a test, right, supposedly, right, teacher says, find X. Student goes, there it is, right, Yeah, I'd probably give some points for that. What's the year 2000? MM, right? So there's not a good correlation between the size of the number and how many symbols you need with Roman numerals. Let's see, this is 2025, so that's going to be what? MM, XXV, yep. 2025, we're in the year MMXXV, et cetera, et cetera. Not that we ever get this large with ionic species, but just just having a little fun here. So, carbon 8, is that a thing?
No.
No, why?
Because it only has 6.
Because it's only got 6 electrons to lose, and that would have been 7 electrons to lose. So not a thing, right? But carbon 7 would be. Carbon 7 is completely ionized carbon. Chemists, I mean, they're so dumb. You know what they would call like doubly ionized carbon? They would call it C++, like, just because there's 2 extra positive charges on it. I mean, come on. Why would you call it that instead of CIII? Stupid. And with that, let's take a break. All right, back to it here. So, finishing up our qualitative understanding, more qualitative understanding of why hydrogen spectral lines are most prominent at a temperature of around 10,000 Kelvin, and it's really not about how much hydrogen there is. We'll do that, and then we'll get into the nitty-gritty weeds. So, first of all, here's your reminder of the hydrogen energy level diagram, right? So we've got the Lyman series, and every time I see this, I can't help myself because this is before your time, but it used to be Sprite, lemon lime soda. They would have this jingle where they said something like, oh my God, I'm going to sing. What is it again? They said, I can't remember the first line, but they go da-da-da-da-da-da-da in Sprite, because Sprite tastes like a lemon. So they said it's Lyman flavored because it's lemon lime. And every time I see the Lyman series, all I can hear in my head is Sprite tastes like a lemon. Glad I could share that with you. Anyway, those are the transitions to and from the ground state. Are any of those spectral lines in the visible? Can we see any of these spectral lines, given that the lowest energy transition in the Lyman series, Lyman alpha, n equals 2 to n equals 1, is 10.2 electron volts? No, those are all in what part of the spectrum? Ultraviolet. Those are all ultraviolet lines. On the other hand, the Balmer series transitions from higher levels to and from n equals 2. The first 4 of them, alpha, beta, gamma, delta, between 2 and 3, 2 and 4, 2 and 5, 2 and 6, are within the visible part of the spectrum. And then the Paschen series, those are all infrared, and then there's bracket full and all not in the visible. So there are 4 visible wavelength hydrogen spectral lines. The Balmer series that involves transitions for the electron that starts in n equals 2 and jumps higher, or jumps down from some higher level to n equals 2. For stellar spectra, we're talking absorption spectra, so we're looking for them being created by hydrogen atoms that start with the electron in n equals 2, absorb one of the Balmer series wavelengths, and use it to jump up to a higher energy level. And so that says, fundamentally, if we want strong hydrogen spectral lines, we need to have as many hydrogen atoms as possible in n equals 2, in the n equals 2 state. But, and again, this is anthropomorphizing. It turns out that hydrogen atoms do not have hopes, desires, and fears. But to anthropomorphize why the hydrogen atoms want to be in the ground state. If you just leave them alone and they're in an excited state, they're going to drop into the ground state. A typical lifetime for a transition, if you kick an electron up to the n equals 2 level, it stays there for about 100 millionth of a second before it drops down to the n equals 1 level. So in other words, it ain't nothing getting hydrogens into n equals 2. Well, one way to do it would be for them to absorb the Lyman alpha line from the ground state, but that's not typically how they're going to get there in a stellar atmosphere. It's going to be via collisions. if two atoms collide with one another, some of the energy in the collision can be used to promote an electron to a higher energy state. And that makes the collision inelastic in that takes away from how much kinetic energy the atoms will rebound with. So, but with collisions, it's not as picky. With a collision, to kick electrons up into n equals 2 from the ground state, you just need 10.2 electron volts of kinetic energy of the incoming atoms, or more. And so it doesn't have to be precise. So typically, it's collisional excitation that will raise atoms, hydrogen atoms in a star's atmosphere from the ground state into n equals 2. But what do you know about temperature? Temperature is, now there's a fancy definition in terms of entropy, but I'm going to do it in terms of the particles without using entropy here, because it turns out that you can also put it in these terms. Temperature is a measure of, it corresponds to the average watt of the particles in, let's say, the gas that has that temperature. As you raise the temperature, what happens on a microscopic level? If you raise the temperature of this room, what happens to the air molecules on a microscopic level? What are they doing differently when the temperature's higher?
Moving faster.
Moving faster, yeah. The temperature is directly related to the average kinetic energy per particle. So higher temperatures, faster motion. So that means that the higher the temperature of the atmosphere, the more collisions will have enough energy to kick electrons from the ground state up to n equals 2. So we would expect that in order to get a population of hydrogen atoms in n equals 2 ready to absorb Balmer series photons and contribute to making those dark spectral lines, the higher the temperature, the greater the fraction will be of atoms in n equals 2, of hydrogen atoms in n equals 2. So far, what questions do you have? So that's like step 1, more collision, higher temperature, more collisions, more electrons being promoted to n equals 2, where they're ready to absorb Balmer series photons. So that's why, if you start out on the low temperature end of the spectral sequence, let's see, OBAF Gookum, what's the low temperature end? Is it O or M that's the low temperature end? M, right? So you go from M stars to K stars to G stars to F stars. You're getting higher and higher temperatures, and also the hydrogen lines are becoming more and more prominent. Why? Because at those higher temperatures, more hydrogen atoms are up in the n equals 2 level, because at higher temperatures, more collisions have enough energy to kick electrons up into n equals 2. So at first, the strengths of the hydrogen lines rise with stellar temperature because more collisions are promoting electrons into n equals 2 in hydrogen, so there's a larger population of hydrogen atoms able to absorb Balmer series spectral line wavelengths in the first place. Okay, does that make sense? That's a big deal there. The higher the temperature, the more atoms there will be in n equals 2. And yet this trend starts to reverse when we get past around 10,000 Kelvin. Because at first you'd think, okay, well then O stars ought to have the highest strength hydrogen lines because they'll have the highest fraction of electrons in n equals 2 because they're the hottest. Except that if the collisions are energetic enough, they can straight off rip the electron off the nucleus and ionize the hydrogen atom and leave it behind as a bare proton and a free electron. So when the temperature gets high enough, you start losing neutral hydrogen atoms to ionization. And a proton that ain't got an electron around it ain't making any spectral lines. Right? So you can't get Balmer series lines or any other lines whatsoever if all you've got is a bare proton instead of an electron able to jump between energy levels. So at high temperatures, you get past A and you go into B and O stars, you're losing more and more of the hydrogen to ionization. I mean, it's still there, but it's protons and bare electrons. So there's fewer and fewer neutral atoms, and so B and O stars, especially O stars, have weaker hydrogen lines than A stars because so many of the atoms have become ionized, not able to make spectral lines at all. The logic of this and the mathematical description of it, which we're essentially going to largely repeat, was laid out by Cecilia Payne. At the time was her name, but later she married Sergei Kapachkin, and therefore acquired another really cool astronomy name from back then, right? She got your anti-jump cannon. Later we'll meet Henrietta Swan Leavitt, right? And Wilhelmina Fleming. There's all these great names. They just don't name them like that anymore. Cecilia Payne Kapachkin, but she was Cecilia Payne when she did this work. This was the subject of her 1925 PhD thesis. So she did this work as a graduate student. She showed, by the logic that I just mentioned, that I just laid out to you, but with the math behind it, that it is in fact temperature that determines the strengths primarily of spectral lines in stars, more so than composition, and that based on her calculations, all normal stars are made almost entirely of hydrogen and helium. And therefore, because, and then, you know, later we see that interstellar nebulae are made of the same stuff stars are, because stars form from interstellar nebulae, the chemical composition of the universe is almost entirely hydrogen and helium. And Cecilia Payne discovered that while she was a graduate student, and it was her PhD thesis. Well, you know, most people, that would make your career, is to determine what is the primary chemical composition of the universe. To show that, you know, nine out of every 10 atoms of the universe is hydrogen and most of the other ones are helium. That's a career accomplishment right there. And it was her PhD thesis, right? And so therefore, this has been described as the greatest PhD thesis ever in astronomy, because it's like, oh my God, what a discovery to make while you're a graduate student, essentially, right? So, right? So, here's the summary then. This is saying what we just said. Call this the Balmer thermometer, so to speak, because the hydrogen lines are sort of a thermometer telling us the temperature of the star. Collisions with atoms and electrons can excite the H electron to an excited state. So it's like Goldilocks and the three stars. Goldilocks wanted to be near a star with strong hydrogen lines, right? And at first she went to a star that was too cool. For temperatures much less than 10,000 Kelvin, very few collisions have enough energy. So most of the hydrogen atoms, it's actually true, well, yeah, most of the hydrogen atoms are sitting there in the ground state. Why? They could make Balmer series spectral lines, but not I'm sorry, stop it. They could make what series spectral lines in the ground state? Not Balmer, but Lyman. They could make Lyman series spectral lines from the ground state, but not Balmer series spectral lines, and that's the one we're interested in here, the visible spectral lines. So very few collisions are energetic enough. Most of the atoms are in the ground state. You ain't making no Balmer lines from atoms in the ground state. And so you get weak spectral lines. So Goldilocks saw that it was too cold, right? Just like the porridge being too cold, right? All that business. You all know Goldilocks, right? That story there. Do you know Goldilocks? Okay, here we go. So Goldilocks and the Three Bears is the story. Yeah, yeah, the porridge story. That's right, yes. So she went to a cool star / porridge, right? That was too cold, right? That's the deal here, right? So then she went to a star where the temperature was a lot more than 10,000 Kelvin, and that star was too hot. The collisions were so energetic in those stars that the hydrogen is basically all ionized. Very few hydrogen atoms are neutral where they can be any spectral lines, and so the Balmer lines are also very weak in such stars. So Goldilocks is like, dang it. So then she went to a star with a temperature of around 10,000 Kelvin, and that one was just right in that you can have a significant number of hydrogen atoms still being neutral, but also bumped up into the n equals 2 state, able to form Balmer absorption lines. And so, not for the coming exam, but for a later exam, I want you to be able to tell this qualitative story. In other words, you know, we're trying to both do math, right, be able to do math problems, but also tell stories, right? Understanding comes from being able to tell stories. And so this is the story of why hydrogen lines are strongest in stars around 10,000 Kelvin. You want to be able to tell this story. There's lots of examples where you could do math I give you, but still not be able to tell this story. And if you can only do the math and not tell the story, you don't really understand it. A classic example, and some of you have experienced me hammering this one home, the photoelectric effect. You can do these, you can easily answer all these questions correctly where you're doing these calculations using the photoelectric effect equations, and still not be able to explain what's actually going on. And this is not acceptable to me. So I want you to be able to tell this story. We're telling stories here. This is an important story to be able to tell. What questions do you have so that you can tell this story later when I ask you to tell me this story?
The title of the story should be
Goldilocks and that is what I will say. Tell me the story of Goldilocks and the 3 stars. I will absolutely say that, yes. And use it to explain why hydrogen lines are strongest around 10,000 Kelvin. I will most definitely, yes, it is. I call it Goldilocks and the 3 stars. And I'm not aware of anybody else. Surely somebody else has thought of that, but nobody told me that. I just thought I'm going to tell Goldilocks and the 3 stars here. So. I'm taking it right now. That's right. That's right. Hey, Goldilocks and the 3 stars. If I see anybody saying that later, I'm going to point to this video and say, hey, they stole this from me. Okay. Unless I find a reference and it's like from 1970 or something, right? Then no, okay. Then, hey, I didn't know. I wasn't stealing it. I independently came up with it. Leave me alone. All right. What questions do you have? Okay, I forget if there's anything else here. Yeah, okay, why not? So, similar considerations for other elements allowed Cecilia Payne to first determine the compositions of stars from their spectra in her 1925 PhD thesis. All normal stars are mostly hydrogen and helium. For our sun, by mass, not by number of atoms, but by mass, 74.5% hydrogen, 23.7% helium, and the rest is heavy elements, about 2% of heavy elements. Anybody know, because astronomers aren't weird at all, what do we call heavy elements? Anything that ain't hydrogen and ain't helium is a metal. Yes, that's right. Everything's a metal except hydrogen and helium. Carbon is a metal. Aluminum is a metal. Aluminium is a metal. Oxygen is a metal. We're so weird. No, we're not. We're reasonable. And so, right, and then the joke then is that the astronomer's periodic table looks essentially like this because we use X to represent, and we'll be getting to this later, capital X is mass fraction of hydrogen, the percentage of the star's mass that is in the form of hydrogen. Capital Y is the mass fraction of helium. And capital Z is the mass fraction of metals. In other words, everything else, stop that, mass fraction of metals. Okay, I need to make that stop. Take me to, yeah, right. Okay, so, all right, mass fraction of metals. So then we have to do this, right? Mass fraction of metals. So here's our story there, mass fraction of metals. And so the astronomer's periodic table is very simple. It's, right, like, and all the other stuff, right? There's X, Y, Z is the astronomer's periodic table. Very simple. Because that's where hydrogen is, that's where helium is, right? You know, all that business. So, boom, that I did not think of. Yes?
Can you say what normal stars are?
Normal stars meaning ones that are either on the main sequence fusing hydrogen to helium in their cores, or are like red giants and stuff like that. In other words, things that haven't died and become white dwarfs or neutron stars, that sort of thing. Yeah, any star that is not exotic or has blown off most of its outer layers as part of its evolution before it's about to turn into a white dwarf, that sort of thing. So any star that hasn't done anything extreme, that has nearly the same composition that it started with, is a normal star from this standpoint. Yes?
What's the difference between percentage by number and percentage?
Yeah, so percentage by number versus percentage by mass. So for example, we see here the chemical composition of the sun's atmosphere. Hydrogen, 74.5% by mass, 92.5% by number, because the mass of a helium atom is about 4 times the mass of a hydrogen atom, right? Because a helium atom is 2 protons, 2 neutrons, 2 electrons, and neutrons and protons are about the same mass as one another. So a helium-4 nucleus is roughly 4 times the mass of a hydrogen nucleus. And so that means you need more hydrogen atoms to produce the same amount of mass as you do helium atoms. And you need more helium atoms to produce the same amount of mass as you do oxygen atoms, for example. So in other words, with hydrogen, 92.5% of the nuclei are hydrogen nuclei, but because each one of them is not very heavy, that adds up to only about 3/4 of the mass. And that's why there's the difference between percentage by mass and percentage by number. Percentage by number is the percentage of the nuclei that are that species. Percentage by mass is add up their masses, divide by the whole mass. That's the percentage by mass. Helium, 7.4% by number. Oxygen, 0.82, so 0.82% by mass, 0.064% by number, because oxygen's like, has 16 times the mass of a hydrogen. And so you can see, and this pretty much is the overall composition of the universe as well, that oxygen is the 3rd most abundant element, but it's not even close to hydrogen and helium, right? Only 0.82% by mass, only 0.064% by number is oxygen. Carbon comes next, then neon, then nitrogen, silicon, magnesium, iron, sulfur. Well, I don't know if there might be others, but I think those are probably the most abundant elements in the list, and then everything else. So one thing is that this ain't random. In other words, why is oxygen the 3rd most abundant element? Well, where do elements come from? The Big Bang made hydrogen and helium. Where does everything else come from?
From the stars.
Stars, right? So oxygen is relatively abundant because stars are good at making it. Stars have nuclear reactions that are pretty good at making oxygen. Similarly, those other elements, their abundances, their relatively high abundances, is because stars are pretty good at making them via nuclear reactions and so forth. Now we'll see that the jeweler's elements, gold, platinum, silver, and the rare earth elements, right? Why are the rare earth elements called the rare earth elements? Because they're rare. I mean, that's, there's not a whole lot of them. Why are they rare? Because stars suck at making them, is what it comes down to, right? It's fundamentally, in fact, the rare earth elements and gold and platinum and silver, a significant fraction of them, most of them, is coming from collisions of neutron stars, which sets off a chain of nuclear reactions involving largely like the the iron nuclei in their crust that build elements heavier than iron. We'll get to more of this later, but it's pretty amazing to me to think that my gold ring here, why is gold precious? Well, 1, it's pretty. 2, it's rare. Why is it rare? Because it's made primarily by neutron star collisions, which is not a common thing to happen in the universe, and so there's not a whole lot of gold in the universe. Everybody should know this, right? I just feel like, most people are walking around not knowing that, and it's like, no, everybody should know. We don't want to be those cows in Hawaii that have no idea that they're on an island in the middle of the Pacific Ocean, right? We can do better than that. We want to know our cosmic context. So we're about that here, and you should spread the word, right? Walk up to random people and say, did you? Well, I haven't started doing that yet. Oh, I'm tempted. I might try it sometime. You know, that's the story of all this. If you cut yourself, that sucks. But on the other hand, there's the blood. It's red because it's got hemoglobin in it. What's at the center of every hemoglobin molecule? An iron atom. Where did the iron come from? Some of it came from the collapse of massive stars that blew up as supernovae. Most of it came from white dwarfs that blew up as supernovae. The white dwarfs were made of carbon mostly, but it was degenerate, and if it merges with another white dwarf or acquires enough mass from a companion star, it can undergo a deflagration event that blasts it to smithereens and produces all of the elements via nuclear reactions up to iron. And so most of the iron in your blood came from exploding white dwarfs, right? If your atoms could speak, then they would have amazing stories to tell. If your atoms do speak, as I like to say, you should lay off the mushrooms. But in any case, there we have it, right? Okay, so, yeah, now shall we get to the nitty-gritty? What questions do you have? Let's get to the nitty-gritty, shall we? Or at least begin getting to the nitty-gritty. Let's see, let me get the screen up because, yeah, we might eventually need it. I'll just leave it there on the side. So, let's see. Okay. So now we're going to put to use all this stuff we said about energy levels and degeneracies and all that kind of good stuff. All right, so following the way the book puts it, we're going to let S sub A and S sub B be the set of quantum numbers specifying two quantum states of an atom. And we've already seen examples of that for hydrogen. A set of quantum numbers specifying the two quantum states of an atom. And we already know for neutral H, these are, we can specify states in terms of N, L, M sub L, and M sub S. And so S sub A could be 2, 1, minus 1, plus 1/2. And S sub B could be 1, 0, 0, minus 1/2 or something like that. So S sub A and S sub B is a list like that. For different elements, you'd have a different list, but for hydrogen, which is a very important element, that would be the deal. Now, we'll let E sub A and E sub B be the energies of the two states. And then I'm just going to assert this. In Stat Mech, you can see why this happens. Physics 320 could show you why this happens, but I'm just going to assert that this is true. Then in thermodynamic equilibrium, in thermodynamic equilibrium, which means that nothing changes in terms of individual atoms might jump between energy levels, and that's constantly happening. But in thermodynamic equilibrium, the fraction of atoms in n equals 1, the fraction of atoms in n equals 2, and so forth, is staying constant with time, except for small statistical fluctuations. So individual atoms are constantly undergoing interactions. But if we look at the system as a whole, the number of atoms in state, say, n equals 2 is staying constant because just as many atoms are entering that state every second as are leaving that state every second. And thermodynamic equilibrium is a condition where that's true. For every possible state, there's just as many atoms entering that state every second as are leaving that state every second, so that the populations stay constant with time. That's a long-winded explanation of what I mean by thermodynamic equilibrium, in case you didn't know that. In thermodynamic equilibrium, statistical mechanics shows, this is a really fundamental result of statistical mechanics. Statistical mechanics shows that the probabilities, shows that the ratio of the probabilities P of S sub B, the probability that any given atom is in state S sub B, and P of S sub A, the probability that any given atom is in state S sub A, the ratio of the probabilities P of S sub B and P of F sub A of finding the atom in one of those two states is given by, wait for it, here it comes. I can hear the drum roll now. Super important result. The probability for state S sub B divided by the probability for state S sub A is equal to the ratio of e to the minus energy of state B over kT, the Boltzmann constant times the Kelvin temperature, divided by e to the minus E sub A over kT, which of course we could simplify as e to the minus E sub B minus E sub A over kT, where K equals the Boltzmann constant, after Ludwig Boltzmann, who pioneered statistical mechanics, the Boltzmann constant. And for us, the most convenient expression of it will be that it is 8.62 times 10 to the minus 5 electron volts per Kelvin. And we'll note then, K has units of energy per Kelvin, right? EV is an energy unit. And so KT has energy units. KT has energy units. And it represents a typical or characteristic thermal energy of particles at temperature T. It's a characteristic thermal energy of particles at temperature T. Of particles at temperature T. Remember, we said that temperature is a measure of the average thermal energy per particle. This is directly related to that. In other words, KT is pretty close to the average thermal energy per particle at temperature T, and in those units it would tell us what it was in electron volts, for example. So at 100,000 Kelvin, the typical thermal energy is about 8.62 electron volts, for example. Because 100,000 times 10 to the minus 5 would, cancel that out. So this gives us a measure of about how much thermal energy particles typically have. And so notice then that e to the minus energy over kT, energy over kT is dimensionless, which it needs to be. E to some power has to be dimensionless. The power has to be dimensionless. And so then what we're talking about then is it depends exponentially on the ratio of the energy of the state to the typical thermal energy. So this is saying that the higher the energy of the state, the harder it is to get atoms into that state, right? In other words, the bigger the energy is compared to the thermal energy, the less probable it is that you're going to see the particle in that state. So this is reflecting this idea that at high temperatures, you'll have a larger number of atoms in higher energy states than at low temperatures. And notice it's a really steep dependence. It's an exponential dependence. And so it's, in a sense, really hard to get atoms to be in a state that has a lot more energy than the thermal energy, than the characteristic thermal energy at temperature T. So, what question do you have so far? So, important to note that a term of the form e to the minus some energy over kT is called a Boltzmann factor. Again, after Ludwig, who came up with this idea. And notice it's representing the relative probability of getting an atom or whatever into a state of energy E given the temperature T. So we want to note that higher energy states are less probable. Higher energy states are less probable. And again, we're not proving this. That's a job for your stat mech class. But we do want to have an intuitive understanding. And that is the reason, well, I'll just read it and then start writing. The reason is essentially that higher energy states are populated by interactions with the environment, such as collisions with other atoms, and given a fixed amount of energy possessed by a gas of atoms, or the solid, or whatever we're talking about, higher energy reactions occur less frequently than low energy ones. But the higher the temperature, the more possibility it is for high energy reactions. So the reason is that higher energy states, I'm going to shorten what I wrote in the notes a little bit to be faster. Higher energy states are populated via interactions such as collisions between atoms, or between atoms and electrons. So I'll just say, etc. And given a fixed amount of energy, high energy interactions are less probable. But the higher the temperature, the more energy you have for having high energy interactions. Now, when you take when you take stat mech, you learn that in thermodynamic equilibrium, you're in a state of maximum possible entropy. Essentially what's going on is there are literally more ways to create the system with a given amount of total energy when things are distributed this way. But again, I'm just going to be like, you know, my proof in this class is, right? Right, some of you seen it, right? Proof by the waving. Those are chicken feet, yes, okay, hand. Chicken feet, right? So here we're just waving the chicken feet and saying this is plausible, and you got to take stat mech to see in more detail where all that's coming from. So, are you at least buying what I'm selling here, and what questions do you have at this point? So let's continue with some gloriosity here, because the thing is, notice that if you've got degeneracy, all the states with a given degeneracy are equally probable, right? Because it only depends on the energies. So if you're looking at, say, the n equals 2 states in hydrogen, they all have the same energy. All that matters, the probability of atom being an n equals 2 versus n equals 1 is just depending on the difference in energy, E2 minus E1, and it doesn't matter which of the substates it's in. The probabilities are the same for all of the substates because it only depends on the energy, which means that the degeneracy must play a role here. It means that we have to account for that. So, let's talk about that. Generally, in the presence of degeneracy, such as at a Cure concert, for example, lots of degeneracy there, says at least some people. In the presence of degeneracy, we are actually just interested in the populations of energy levels. We don't care about how many are in n equals 2, L equals 1, m sub L equals 0, m sub f is minus 1/2. I don't care. I just want to know how many are in n equals 2. So we are interested in the population, in the relative populations, because remember, this is a ratio of how many are in one state divided to how many are in another state. So that's what I mean by the relative populations, the ratio of how many in state 2 divided by how many in state 1, as opposed to, although we can do this sometimes, how many in state 2 period, how many in state 1 period. We are interested in the relative populations of different energy levels, as opposed to the individual states comprising a given energy level. As opposed to the populations of the substates. E.g., right, which stands for example, e.g., how many atoms are in n equals 2 versus n equals 1. How many H atoms are in n equals 2 versus n equals 1. Who cares about L, ML, MS, not us. Although really the answer is if the degeneracy is 8, 1/8 of them are in every one of those substates because the probability only depends on the energy in the end. So one more thing to do before we're done here, and then we'll take this and run with it next time. It's going to be glorious. We're going to trace Cecilia Payne's steps. It's going to be glorious. I love it. In this case, we have that the probability of finding an atom in energy E sub B divided by the probability of finding an atom in energy E sub A, which will be the same as the ratio of the actual number of atoms in in state B and the actual number of atoms in state A, right? In other words, if any given atom has a certain probability of being in a state, that times the total number of atoms would be the total number of atoms in that state. So the ratio of these probabilities is also the ratio of the actual number of atoms in state E with energy E sub B. Actual number of atoms with E equals E sub B, and then likewise on the bottom there, it's equal to the same thing we had before, except we have to multiply by the degeneracies. The degeneracy for energy level E sub B times a Boltzmann factor, e to the minus EB over KT, divided by the degeneracy of state A, e to the minus energy of energy level A, e to the minus EA over KT, or in other words, it's Gb over Ga times e to the minus energy level difference, the delta E, the energy gap between the two states, over KT. Wow, is this ever a box-worthy equation? And what are we going to call this equation? We're going to call this the Boltzmann equation. Ta-da! The Boltzmann equation. My chalk is not cooperating. Wow, it's really getting, okay. The Boltzmann equation. Boltzmann equation. Ooh. We're going to take that and run with that next time, and then we're going to combine it with the Saha equation and explain Cecilia Payne's findings, basically. So it's going to be great. And if you could have done that in 1925, you'd be famous too. But you can do something else to be famous. Okay. Any questions before we stop? What questions do you have? Could this be any cooler, I hear you saying? No, it could not. It could not. It simply could not. Actually, it's hot on some level, too. It's both hot and cool.
So exam is on Monday then?